This lesson is about optimizing deep learning, where we will see much deeper into the deep learning uh, in its implementation. Basically, implementation means how uh, the real world problems arise in the deep learning and how they are handled. Right? Actually, we are not going to discuss about the coding part, but we will see the theoretically and the practically how the deep learning was implemented and what are the problems that are there and how the optimization part in the deep learning was developed in several ways. Right. So the in the first phase of this lesson, we will be discussing about the main problems that we have in deep learning and how they are solved. And then the second part of the lesson, we will be discussing about the optimizers that are developed. Optimizers means the developed versions of gradient descent algorithm, basically how they are how they are designed based on what kind of concepts, right? So before that, we can start with the basic theory related to the scaling, right? If you are not that familiar with scaling, with related to gradient descent, this is how it looks like. Okay. So when it comes to the features of a machine learning problem, basically, even though it is a deep learning problem or any other machine learning problem, we say that the features that are used in that learning problem should be scaled, right? Something like this. So this is the 3D visualization, and this is the contour graph, which is the 2D projection of this 3D visualization, uh, which is the cost function change with respect to the uh, weights and biases. Right? So actually, there are in the real world, there's only not only a single weight, but there are multiple weight dimensions. So it would be uh, having many number of dimensions. So because we can't visualize this in multi-dimensional space, we have just used three-dimensional space where you are seeing one dimension for bias and one dimension for weight. But this is weight. This W is actually vector. It would contain many dimensions, right? So if we say this is S as a single dimension, so then we are trying to find what is the so the other dimension is the cost function, which is the J function, where we are trying to find the minimum cost function, right? That is the idea of mm, the optimization in deep learning or any the machine learning problem, right? So once we project the two types of the normalized or non-normalized or unnormalized cost functions, right? You can see these different contour graphs. So when you have features that are not normalized or scaled, you will get a cost function contour graph like this, right? Which is not a symmetric one. But when you have scaled uh, scaled all the features so that each of the unit length of the W vector, for example, is corresponding is equal to the or representing the similar weight of the unit distance in the bias uh, dimension, right? So if there's another dimension, this dimension, that particular dimension would also represent a unit distance in that particular dimension, which is having the same weight as the other weight vectors, right? So in that case, you will get a contour graph which is very symmetric, right? So when you have two dimensions, you will get a set of circles inside one of each other, so that you can see that when you are training this kind of mm, wait a minute, when you are using this kind of sorry, when you are using this type of contour graph of the cost function, you can easily, in when it is training, so suppose that you have started training here, and the training would happen like this, right? Simply it can move very faster towards the final solution. But when it comes to this kind of uh, contours, if we unfortunately if we have started somewhere here, right, so it would move here, there, and so on, right? So if your other hyperparameters are correct, so you would finally move towards the final solution, but it would take a lot of here and there movements, right? Instead of moving to the say to the optimal point, right? So if you start here also, you will move here and there because your algorithm will not clearly understand where you should move because the gradients are not having a clear path to follow in this kind of scenario. Right? Because of that, it is very good if you can scale your features, right? So that is the idea, right? And I have started with this theory because we will need to remember why we are scaling features, because in so one reason is for the purpose of having a good optimization uh, path when it comes to the gradient descent algorithm, right? So there are several other reasons as well, but for the moment, just remember this is one of the most important reason that we need, uh, why we need to have scaled features in our deep learning algorithm, right? So let's move into the problems that we face in the deep learning algorithms. So we have discussed about shallow neural networks, and we have also discussed about deep neural networks. Compared to the shallow neural networks, we are facing some problems when we increase the number of neural layers in a neural network when it comes to deep neural networks. Basically, these problems are related to the training process during the backpropagation uh, algorithm, right? When we do the backpropagation algorithm, we have to calculate the gradients and in the from the final layer from the cost function, and then they have to be moved towards the inner layers uh, in the backward direction, right? As we have discussed, right? Using the chain rule in the calculus, you have to move the uh, gradients to the inner layers one by one to update the weights in the neural network, right? If this is the neural network, if these are the neural network layers and this is the X inputs and this is the output, right? So you have to start with the output uh, cost, right? J cost, and then we have to move towards the inner layers to update the weights in each of these layers, right? So when you have many number of layers, you will face some problem. One problem is known as the vanishing gradient problem, right? And the other problem is known as the exploding gradient problem. These are one of the major problems that we face during this training process in backpropagation in deep neural networks. So this vanishing gradient problem is actually about the gradients are getting uh, less and less when we are moving towards the uh, inner layers, right? And yeah, the gradients are getting like vanished, almost vanished, and moving towards zero when we are moving inside the layers. Right? So when we have many number of layers, this problem is getting critically important. So with this problem, you will not be able to train many number of layers, so your potential architecture of the neural network would be limited only to several layers, right? But after, once you have taken some actions, taken some solutions to this problem, you can actually add many number of layers so that you can increase the intelligence of this neural network. Because we have discussed that when we increase one layer, you can exponentially increase its learning capacity, or the, like, it is equivalent to number of neurons in a single layer, which is exponentially increasing when you increase the number of layers, right? So that can be achieved when you can add more and more layers. But in order to add more and more layers, you have to solve, you have to mitigate this problem of vanishing gradients, right? So we will see why this vanishing gradient problem happens and how it can be uh, mitigated or resolved, right? So the opposite of the vanishing gradient problem is known as the exploding gradient problem, right? Where the same problem is, where during the backpropagation we are training from the cost function, the last layer to the earlier layers. But in this case, our gradients are not getting vanished to the zero, but they are getting uh, exponentially increasing more and more, so that the gradients are getting so large, so that the numbers that have to be uh, the gradients that has to be uh, updated in each of these layers will get too large. So when it comes to a computer, you should know that there are some limits that you can store a particular number, right? So say, like, you can uh, have a very large number inside a certain, like a 32-bit or 64-bit uh, memory space, right? So in that case, this memory space is running out of memory when the gradient is increasing so much, so it would having some technical problems, and it would not be possible to learn, uh, move forward. That means you can't learn further layers when your gradients are getting so large, from this layer to the other layer. So for example, this layer, it would be like this, the gradients. This layer, it would be like this, and the next layer, it would be like gradients would be like this, and so on. So then this size would be too large so that it can be learned furthermore, right? That is also a problem with deeper neural networks. So although these vanishing gradient problems are exploding gradient problems seemed opposite to each other, uh, they are getting, so we don't know which should happen, right? But taking some actions for both of them, you can, with higher probability, you can assume this problem will not be there in your neural network. First, look at the vanishing gradient problem that you see in deeper neural networks. So as you know, the problem is about the gradients are getting reduced, diminished exponentially as they backpropagate through the layers, right? So why does it happen? This is mainly because our sorry, our activation function, which is a nonlinear activation function like sigmoid or tan h, is having diminishing gradients when it comes to larger positive numbers and larger negative numbers, right? For example, if you take this sigmoid function, right? This is Z and this is sigma Z, for example. We know in the sigmoid function, if this is 1 and this is 0.5, right? So the sigmoid function would be something like this, right? It would range in between 0 and 1. Right? In the region around 0, you will see there's a high gradient, right? In this region. But when we have very larger positive values, something like this, right? You would have a very small gradient, right? Gradient. And when we are having a very large negative numbers as well, right? You would see a very small gradient change in this region. Right? When you are having the backpropagation, running the backpropagation algorithms, if the sigmoid function falls into these regions, this gradient changes would not be so significant, right? So in that case, if the z is getting higher and higher, these gradients would be diminishing more and more towards 0, or if the negative z values are getting higher more and more, these gradient changes would be diminishing towards 0, right? So if that kind of scenario happens in layer by layer in the deeper layers, you will see that the gradients would be arriving to the 0 when we are moving towards the layers. The same happens with the tan function as well, right? This is 0, this is +1, and this is -1, right? Uh, this is Z and this is tan h, right? Tan h of Z, right? So it is also similar to the sigmoid function, right? The only difference is it is ranging in between +1 and -1, right? The same problem would be there in the tan h function as well, where a significant gradient can only be observed in the range around 0 in the Z, right? When it is too large, uh, when it is a too large positive value, or when it is a too large negative value, the gradients would be significantly low, right? So when you are moving into the back layers, into the inner layers, if you face uh, with higher Z values, or higher positive Z values, or higher negative Z values, the gradients would be moving towards 0, right? So by looking at these functions, you can see that you can tell that this may be mainly due to the uh, nature of the sigmoid and tan function, right? Actually, this is one of the main reasons that we couldn't add more layers. Uh, that means when it comes to the earlier time in the deep learning, we couldn't increase many number of layers, so that we couldn't achieve the current level of technological improvements in the deep learning when we were using these functions. But as when we have found this tan function, where you can have, so if this is Z, and when this is a ReLU function, right? ReLU Z. So it is a very simple function, right? It is greater than 0, the value is equal to Z, right? So this is a straight line, right? And if the Z is lesser than 0, the ReLU value would be 0, right? This is the 0. In this kind of activation function, you would neither uh, when you whatever the value that the Z would have, if it is positive, the gradient would always be 1, right? So in ReLU activation function, when the Z is positive, the gradient is always 1, right? What, but whatever the value the Z would be, right? So that is the advantage of ReLU function. So once the ReLU function the ReLU activation was found, we could add many more layers into the deep neural network so that we could, there was a breakthrough in the field of deep learning when the ReLU function was found. So that is how the vanishing gradient problems are affecting to the uh, learning of deep neural networks. So now let's move into the exploding gradients, which is the opposite of the uh, vanishing gradient problem, right? So in that case, as we have discussed, the gradients are getting increased more and more due to the uh, increase of gradient, so that it would, the earlier layers would have very large numbers for gradients so that they can't learn, right? Because there are some limitations in the computation infrastructure to keep the gradients and the values, so that these values will not be able to handle very large values, so that this the digital value number would be overflow. There would be an overflow condition where you won't be able to keep these values in a memory location, so that it won't be able to process. That is the main problem with exploding gradients. Actually, this can also happen due to uh, some uh, due to some other reasons other than this activation functions, basically, right? So if we are using an activation function like ReLU, like sorry, like sigmoid or tanh, you will find that it won't be having the exploding gradient problem, because the highest gradient would be around 0. So in the other regions, this gradient would not be that much significant. But when it comes to real world problems, so if you are having very large initial values, for example, initial values means when you are training the neural network, you have to set the initial weight values, which is initialized from a random number, right? If these values are too large, so then there would be a problem in some situations, right? Actually, we don't know what would be the numbers. We can't predict, but there can be situations where the numbers would be higher in the uh, deeper layers, right? So this can also happen with the ReLU activation function as well, because in the ReLU activation function, although the gradient stays the same, but because the numbers can get higher and higher, and the gradient can also increase with the number of layers in some situations. So in order to uh, uh, address this gradient, exploding gradient, there we have to do some other different types of precautions to avoid or mitigate the exploding gradients. So in that case, the ReLU is also a good solution, but using the ReLU activation function is not sufficient. But you have to think about other cases, like initializing with correct set of initial values. So in order to uh, mitigate the exploding gradient problems, the main option for mitigating the exploding gradient is using initializing the weights in the correct way, right? So there are two, basically well-known two types of initialization techniques, known as Xavier initialization and He initialization. And so we will be discussing uh, after a few minutes, and this can actually handle the problem of exploding gradient mainly, and also this can also handle uh, some form of vanishing gradient as well. And when the gradients are getting too large, the problem is not being able to process using a computer. So one of the options is clipping the gradients when the gradients are getting too large, right? So that may not be a solution when we need to update the gradients in the previous layers, but at least you can make sure that the gradients are not getting increased too high, so that the earlier layers can, the later layers can learn, so that uh, this particular gradient is getting higher, and we can continue using the gradient clipping technique. In the gradient clipping technique, we are having a hard bound in the when it comes to the gradients, and we stop the increase of gradients without allowing it to grow into a very larger number, right? So that is what we are doing with gradient clipping. We are not allowing, we are having some clipping points, like so we will see how we do it in correct way, right? And so in that case, we are using some predefined thresholds for the gradient value, so that these values would not be exceeded when we are propagating the gradients. And also we can use the, as we have discussed somewhat a few minutes ago, we can use the ReLU activation function or similar activation functions, where the uh, gradients are not getting diminished, to mainly to reduce the uh, issue of vanishing gradient problem, right? So there are some other techniques as well, right, for handling the vanishing gradient problems and exploding gradient problems, uh, which is about the normalization, right? The concept of normalization is about uh, us, the people who are developing this neural network should have some understanding that these parameters should be following some normal distribution. So if you think that that a certain parameter is having a normal distribution, we can uh, make sure that this particular distribution is should be adherent to a normal distribution, so that we can learn, and we can limit our learning so that it will not go far away from the normal distribution, right? For example, so it can not having very large a number, so that it would not be having the problem of exploding gradients, or should not be having too smaller values, so that it would not be having vanishing gradient problem, right? In that case, what we are trying to do is we are trying to uh, optimize it into a normal distribution in different ways, right? So the one way of normalization is known as batch normalization, where when we are taking a mini batch or the full batch, we are assuming that a certain parameter in a certain layer is following an normal distribution when it comes to a data set, right? Or mini batch or the full batch, right? We are assuming that when it comes to the all the data in the mini batch, right? So this is the number of data, right? The distribution would be following a bell curve, right? So this is a bell curve, right? So okay, my bell curve is not nice, right? So here, what we are trying to do is we are taking the small mini batch basically, right? So when it comes to real world deep learning problems, we are using mini batch gradient descent. That means we are using a you are taking mini batches if you are having too many number of uh, data points, or you can use stochastic gradient descent as well, right? So for smaller data sets, you can use batch gradient descent. But when it comes to batch normalization, what we are trying to do is we are assuming that the data points in the batch are following a normal distribution when it comes uh, to a value related to a certain parameter in the neural network. So when you take a certain weight, for example, or the certain value, it should be, or the output value, right? They should be having a normal distribution when it comes to all the data points for each of the data point in the mini batch. Right? That is the idea of batch normalization, and we will discuss how it is done in the mathematical way. Right? So in the layer normalization is that not we are not focusing about the mini batch that we are going to train, but we are focusing about the uh, neurons that we are having in our current layer of neural network. Right? So if we have 4 neurons, we assume that each of the 4 neurons would be having a normal like distribution when it comes to the values uh, in this particular layer. Right? So when we are updating these values, we are trying to fit to the normal curve when it comes to the uh, neuron related parameters in each of these layers. Right? So that is another. So this batch normalization and layer normalization are some other techniques so that you would not be having too large values or too small values. So we are doing each of them in each of the neural. So when it comes to batch normalization, we are doing it in the weight basis. When it comes to layer normalization, we are doing it for uh, neural layer uh, by layer application. And in this case, we are trying to avoid the values are getting too larger or too smaller by uh, trying to fit them into a normal curve uh, that we assume that the value should be. Right? That is the technique of using batch normalization and layer normalization. So we will be learning about this in detail in upcoming slides. Right? And also instead of using so we will be learning these things later, which is about recurrent neural networks and LSTMs and GRUs. Uh, when it comes to the recurrent neural networks in its basic format, we will have this exploding and vanishing gradient problems, and different types of gated units were developed so that these LSTMs and GRUs were developed with different architecture so that this vanishing gradient and exploding gradient problems were not observed. Actually, this could be minimized. So still, when you are using too long or too deeper neural networks, these problems would arise. Right? So, so these problems are there in this deep learning world when it comes to uh, all the almost all the neural networks, right? So we will be having different forms of addressing these exploding and vanishing gradient problems in uh, this deep learning subject, right? So now let's move into the weight initialization, uh, which we are how we do the weight initialization and how to do it correctly, right? So if when we say that how we are going to initialize the weights in a neuron, right, in a neural network, so we said that other than the bias term, you should not be having zero initialization for the other weight vectors, right? So in the for the other weight values, right? Uh, so the recommended way of initialization of these weights in a neuron is using a random distribution. Right? You should initialize each of these weights in a neuron in a random way. Right? But if you take say these are the W1, W2, and Wn are which are the weights of a neuron, and x1, x2, xn are the inputs of the neuron, and y hat, which is the is the output of the neuron. And if before we apply the a, so we will be having an z value, intermediate value, right, inside the neuron. So this Z value would be having a relationship like this, right? X1 W1, X2 W2, Xn W. So once you apply the sigma to a Z, you will have the activation value, right? So this Z value would be increasing when your n is increasing, right? Is that clear? Say that weights are initialized having a certain mean, right? So when you have large number of n values, then these W terms are also getting, so this, when the weights are, number of weights are getting increased, if the dimensionality is getting increased, this Z value will also get increased, right? So that means when with with the value of n, or the number of inputs, this Z value will get increased, right? So that is a problem which would cause the exploding gradient problem, right? So what we can do is we can actually uh, reduce the total weight of this Z value by uh, dividing the variance of the weights, right? So what we do is, when it comes to the ReLU activation function, they have mathematically found that if you are using 2 by n, and if you divide this, divide all these weight values by, so actually you multiply with 2 and divide by n. N is the number of uh, features, number of dimensions, right? Then your weights would be reduced to a certain level, so that it would be not be having a very large value with the number of n, right? So that is known as the principle of HE initialization, right? So that is when you are using the ReLU activation function, right? And we also said that sometimes we can use the tan H activation function as well for the inner neurons of a neural network. So in that case, you have to, instead of using 2 by n, you can use 1 by n, or actually what you are trying to do is you are just dividing these weight values by number of uh, weights, so that the weights are reduced, right? That is another way of initializing these weight values, right? Actually these weight values are W1, W2, Wn are randomly initialized, right? So instead of just applying it to these randomly initialized value to the as the initial values, we multiply either with 2 over n or 1 over n for initialization, so that it would not be having two larger values for weight values, which would lead to exploding gradients, right? So when it comes to the tan h, when you multiply with 1 over n, and this is known as the Xavieror initialization, right? For the ReLU activation function, it would be known as HE initialization, and when it comes to when you are using 2 over n, and for the tan h initialization, you multiply it with 1 over n, which is known as the Xavieror initialization. So these are experimental values, and they have shown practically as well that when you are initializing these weight values multiplied with these terms, or actually reducing the weight values depending on the value for n, you can avoid the probability of having exploding gradient problems in most of the neural network problems, right? So actually this instead of using the exact H initialization or Xavier initialization, you can decide which value you can use for updating these weight values for initializing, and it can be also considered as a, or this variance. So we assume this should be having a certain variance in each of these weight values, and that is how we have calculated this 2 over n or 1 over n, right? Uh, Depending on the activation functions. So this variance is also a hyperparameter, right? So we don't know actually what this variance is. So if you want to further fine tune a neural network, actually you can change this variance hyperparameter as well, right? So this can be used for. Uh, so if you are using two smaller weight values, you would be having uh, vanishing gradient problems, and if you are using two larger values, you would have exploding gradient problems. So when you're using this dividing function, you would mostly addressing the problem of exploding gradient problem, right? So this is the technique of using gradient clipping, right? Actually, we can clip the gradient in two ways. The one is using the maximum and minimum threshold, right? For example, if you say this is uh, these are the gradients that you have, right? So plus 0.9, plus 3.2, plus 150, minus 2.1, and plus 0.3, right? So say that you are having a maximum and minimum limit as plus 1 and minus 1, right? The plus 1 plus maximum value is plus 1 and the minimum value is minus 1, right? So if that is the case, you can say that 150 and 3.2 would be clipped at 1, right? So this value 3.2 would be mapped 1.0 and 150 would also be 1.0, right? So the value which is negative 2.1 would be clipped as the minimum value, which is negative 1.0, right? All the other values would be mapped to the same value, right? So positive 0.3 and positive 0.9 would be mapped as they are, right? So that is one way of mapping the gradients using the gradient clipping technique using maximum and minimum thresholds. The other technique is clip by norm, right? In that case, you are normalizing the gradient vector uh, and have the maximum and minimum thresholds, right? So in that case, so if suppose this is the same input gradient vector, and in that case we are normalizing between maximum and minimum value between plus 1 and minus 1, and in this case you get this kind of weight vector. So you will be once you calculate these mean values and standard deviations, you will see that this value, the plus 150 would go around 1.0 and the minus 2.1 would be a negative value, which is not exactly the negative 1, right? So which is a negative value, and the other values would be having smaller positive values, right? This is another way of mapping the gradients into a range so that it would not be exploding to a very large value, right? So we have also discussed why we are using uh, a proper activation function, right? Where when you are using a sigmoid or tanh activation functions, there would be problems, right? Uh, and we can use some activation functions such as ReLU, which is known as the rectified linear unit, or some variants of ReLU activation function like leaky ReLU or exponential linear unit, or SALE, which is about the scaled exponential linear unit, and so on, right? Okay, so now let's understand what is the batch normalization, what we have just explained, right, into further detail, right? So so what is batch normalization is that we have learned so we say that when it comes to x input, right? So x is the input for a certain variable, right? And it is trying to uh, assume that this x variable uh, is so in the very first parts of this lesson we have learned that the x variable, right, uh, or an input variable, once it is scaled, right, in a certain way it is easy to learn, right. So in the very first way, that in the visualization we have seen that when the x variable, so when it comes to x variable, actually it is a x is a vector, right. So when the x vector is normalized, that means the each unit distance in x1, for example, is equal to the uh, unit uh, distance of the x2 variable. That means uh, x vector is normalized, right, or scaled, right. So normalization is one form of scaling, right. So if you can scale the input uh, vector, you can learn easily, right. Similarly, when you are having a deep neural network as well, in each of these neural layers, you have certain vector similar to this x vector, which is used for the input as well, right? So x is a vector that is used for the input, and there are some other vectors as well, right? Like z vector, right? So when you are moving from here to here, you are calculating the z value, right? Then you calculate the activation value, right? For each of these layers, right? So from out, as the output of this layer, you calculate the z value and the activation value. From here also you calculate the z value and the activation value. So in each of these layers also there can be vectors similar to the x vector, and if you can normalize or scale these z values or activation values, you can learn easily in each of these layers, right? So in this case I am trying to isolate each of this layer independently, uh, and trying to understand that if you can scale each of these layer outputs independently, then you would be able to learn much more easily, like that we have seen in the input layer x, right, in the first slide, right. So what we are going to do is we are going to scale these z values or activation values in each of these layers independently, so that each of these neural layers can learn uh, in a much more robust way when it comes to the gradient descent optimization, right. When it comes to this scaling, we are normally using the normalization, and we are actually using uh, generally we are using the z value for activation for normalization, and we will see how it is done, right. So once you are using this batch normalization, you can actually uh, limit your variable value within a certain range, so that those values would not be getting too large and too smaller, which is also, as you might remember, that it would be a regularization technique as well, right. So this regularization effect is known as the implicit regularization. We are not using the batch normalization as a regularization technique, but implicitly, that means once you are using the batch normalization, there would be a regularization effect as well, right. So when because these z values, we are not allowing each of these z values or the activation values to not to go from a certain range, that would be having a regularization effect, and also that would help to learn much more easily, and because they are not moving uh, in a wildly, so right, so that would reduce the probability of having exploding gradient and vanishing gradient problems as well, right. So this applying this normalization to each of these layers independently is known as batch normalization, right. Actually you are using this you are applying for each of these data points. So in this notation, right? So when it comes to the zi means for the ith data point, right? So for each of these data points, you can calculate the mean value, right? For, for the mini batch, right? For the mini batch, you are taking the sum of all the z values and divide by the number of data points, and you get the mean value. And similarly, you can, for each of these data points in the batch or the mini batch, you can use the calculated z calculated mean value and take the squares of them and divide by the number of data points, and you will get the standard deviation of the batch or the mini batch, right? And then you can use this standard deviation or variance here and use the mean as well here, and you can actually calculate the z score, right? So this is known as so this z is actually the z output for ith data point, right? So this is actually the z score of this z value, right? So this is the z norm or the normalized z value. Actually, this is the z score uh, of the z value, right? So that is, so don't get confused with this zi, right? This zi is about the z output from the neural layer, and this is the normalized z score, right? Normalized z value in that particular layer, right? So the only difference from the z score is that you have this epsilon value, which is very smaller value, something like 10 to the power minus 8 or something like that. So this is used for uh, computational requirement, where this is also known as numerical stability. That means if in some case, if this sigma goes to 0, then this calculation would result like this something divided by 0, right? So then there would be a computational error. So in order to avoid this error, you add in this epsilon value, where this denominator would not become 0, so that it would be a very smaller positive value, so that uh, there would not be any computational issue when you're calculating this normalized z output, right? That means for each of, in here you can see, for each of the data, each of the z value, you are calculating this normalized value, right? However, this zi norm, which we have just calculated, is actually a z score, right? So what is the nature of z score? You may remember, right? So z score is actually a value that is having a a standard normal distribution, right? It should be having a standard deviation of 1, right? Standard deviation of 1 and standard deviation of 1 and mean of, or the average of 0, right? But when it comes to the z outputs of a certain layer, these values are not always 0 when it comes to mean, or the standard deviation is also not equal to 1, right? Because of that, we can't directly use this normalized z value as the output of, as the z output, right? Because of that, we have to uh, add two other parameters, gamma and beta. Actually, these parameters are learned during this backpropagation algorithm, right? So these are some values that we are learning through the backpropagation algorithm itself, and we are using this z norm here and multiply it with this gamma value and add the beta value, so that you will get the z tilde I, right? Which is not a standard value, but which can have a normal distribution which is not a standard normal distribution like what we had in ZI norm, right? So in that case, we have to learn this gamma value and beta value through the backpropagation, right? So in each of the layers, now you understand, we have to learn these two parameters as well during the learning process. So when you are uh, learning these two parameters, gamma and beta, you will see that this beta parameter especially will also include the information with related to the bias term B as well, right? So when it comes to learning a certain neuron, right, what you generally do is you learn both weight W and bias B as well, right? This bias is independent from these inputs, right? It's a constant. But now this beta also includes the information related to the B. So from here onwards, we don't need to. So once you are using this batch normalization, you don't need to learn bias B in the neuron, right? So you have to only learn the W but not B, right? So, so when you are using batch normalization, the parameters that you have to learn are weight vector for the, this is for the Lth layer, right? So for the Lth layer, we have to learn the weight vector for the Lth layer and the beta values, right? So for each of the neuron, we have to learn the beta values for the layer, and also you have to learn the gamma parameter for each of the layer as well. We don't have to learn the B values for the Lth layer, right? So you don't have to learn bias values because the same information is learned by this beta constant value, right? Because this is independently calculated, right? Which is not a multiplication of ZI, right? So I am not going into mathematics, right? So just remember this beta is also learning the same information related to bias, so you don't have to learn the bias in each of this layer. Instead, you only have to learn these three vectors in each of these layers when you're using batch normalization, right? So before the batch normalization, we were having to learn WL and BL, right? B means bias for the L. Now instead of bias, we are learning beta L and gamma L, right? Actually, beta L is also in learning the same thing, right? The same information like the BL, right? So now we are learning WL, beta L, and gamma L for each of these layers, right? That is how the batch normalization happens. So now let's move into the layer normalization. So in the layer normalization, you don't have to learn the same thing again. What you have to understand is that the layer normalization is same as the batch normalization, right? Layer normalization is same as the batch normalization, except the batch normalization normalized across the batch, right? Or the mini batch, right? That means for the in batch normalization, we are taking the statistics in the batch or the mini batch of the data set, right? But when it comes to layer normalization, layer normalization normalizes across the feature dimensions within each example independently. That means feature normalization sorry, layer normalization happens in the layer parameters, right? Not in the data batch that is used for training, right? So we in the layer normalization, we are assuming that the parameters in a certain layer should be having a normal distribution, other than assuming compared to the batch normalization, where we are assuming that the data points in a batch should be following a normal distribution. Right? So we apply the same calculation, same techniques, same learning principles like this gamma, beta, and so on, and this averaging, standard deviation, calculating the norm, and this gamma, beta, and these learn parameters without b, so not b, right? So all of these are applied to. So actually, this is not b is not there, right? So this is applied for the layer normalization. The only difference is that instead of using the data batch, we are using the parameter values in the or the values in the respect to each of the layer in a neural network, right? So why we are using layer normalization? Actually, when it comes to recurrent neural networks, which we'll be discussing later, or in transformer neural networks, right? So it should be discussing even later, right? So in those cases, we are using layer normalization. When the one of the reasons when you are using layer normalization or batch normalization is when there are some, for example, if when the problem is time series problem, something like that, right? So when there are some cases where we can't assume that the distribution in the data set is not a normal distribution, but because there can, when it comes to RNN data set, there can be uh, situations where the close by data points are related to a certain distribution, not a normal distribution, right? So in that case, you will not be able to use a batch and assume it as a normal distribution, right? So in that case, you can't use batch normalization. So you can use layer normalization instead, right? So instead of, so the batch in the layer normalization, you don't have to think about the batch, but you are thinking about the individual layer independent from the data set, right? So you are trying to normalize the features in the layer in each time step, right? So you don't have to think about the whole data set, but you have to think about the layer features in each of the time step or the each of the example or the sample data point, right? For each of the data point, you have to calculate the uh, layer normalization. So layer normalization can be more computationally expensive compared to batch normalization, right? Because for each of the individual data sample, you have to calculate the layer normalization. Where in the batch normalization, you have for the set of data points in the batch or mini batch, you have to calculate the mini batch normalization. So why layer normalization, when layer normalization is not good, is when you are using convolutional networks, so which we will be discussing later as well, right? So in convolutional neural networks, batch neural batch normalization works better because when it comes to close by data points, it contains the information uh, which is related to, which is much more related, right? Compared to the layer wise information, right? So in some cases we are using batch normalization, some cases we are using layer normalization. So you have to use them appropriately. So people have experimentally verified in which cases we are using layer normalization, when we are using, and when we should be using batch normalization, right? Okay, we have learned about the first part of the lesson where we have learned about the normalization, that is sorry, the problems, basically the way vanishing gradient problem and the vanishing gradient problem and exploding gradient problems, and how to overcome them using some techniques. And now we are going to learn about the second part of the lesson, which is about the optimizers that are used during the learning process, right? So when it comes to optimizers, don't think too much what is the meaning of the optimizers. The simplest and the most basic optimizer that you know is the gradient descent optimizer, right? Gradient descent optimizer is the most basic optimizer that is used for learning a neural network, right? With time, so people have found there are certain downsides in the gradient descent optimizer, so that you can improve them, and they have time with iteratively with with the advancement of the subject, people have developed this gradient descent optimizer using some other heuristic concepts, which we'll be discussing later. And using these heuristics concepts like the momentum and so on, exponential moving averages and so on, they have found better ways to learn. That means without having too much rough paths like we have discussed during the stochastic gradient descent and so on. And instead of having to learn uh, through highly varying gradients, where the optimum value would not be having faster, right? Especially when there are many number of dimensions, right? Some dimensions are varying high. That means they are having higher gradients, and some gradients are having lower gradients. So how to deal with them, right? So the gradient doesn't handle each of these uh, dimensions independently, right? So you have to independently update the learning rate of each of these uh, gradients in each of these dimensions, right? So these concepts were included into the gradient descent algorithm, and they have developed different forms of optimizers with time, right? So we will learn what are the later versions of gradient descent optimizer, basically, right? So there we don't call them as gradient descent optimizers, but by their names, uh, which we will call them in later, right? So for reminding you about this gradient descent optimizer, this is how it works, right? So the gradient descent, which is also known as GD, right? Is the most fundamental optimizer, right? And it updates the weights in opposite direction of the gradient, right? So this is its update rule, right? So in this case, so from here onwards, I am using the convention of using theta as the model parameters, right? So this theta is not a single parameter, but all the parameters with related to that particular model, right? Or the particular layer, basically, right? Or particular neuron, right? And how these theta values are getting updated is so that its original values will be reduced by uh, the gradients. This is the gradient of the cost function, right? So with this delta theta, that means when the cost function uh, take is applied with the gradient op operator with the parameters of theta, right? So this is the gradients or the gradient, the parameters of theta, right? So these are the gradients, and we multiply these gradients with this learning rate, right? So this is the learning rate, which should be around 0.01 in general, but it can be changed, right? So this is what we have learned about gradient descent optimizer. We are updating this theta value by reducing the gradient value multiplied by the learning rate, right? Now we are going to improve this gradient descent optimizer with further innovation, right? We have also learned about uh, the versions of gradient descent optimizer based on the batch size that is used during the updating phase of the parameters, right? So if you are using all the whole batch for updating the parameters, that is known as the batch gradient descent, right? We have learned that during the batch gradient descent you can follow a smooth learning curve where you can smoothly move towards the optimum point without having too much uh, rough movements here and there in the learning path, right? But the problem with this batch gradient descent is that you would have to compromise a lot of computation power because we have to go through all the data points in the batch. So this should not be practical when it comes to larger uh, data sets, larger training data sets, right? So when you are having a very large data set, you can use stochastic gradient descent instead, where uh, you are using each of the data points for updating the parameters. But the downside is that uh, uh, the upside is that you can learn faster, right? And the problem is that the updates would be noisier, right? And there would be some instability in the intermediate states of the learning process, right? Because you would be having a lot of here and there movements when it comes to learning through the contours, right? Instead of moving like a smooth curve like this in the batch gradient descent, right? But there's another advantage in the stochastic gradient descent as well, right? So that is known as the um, regularization effect, which is implicitly available in the stochastic gradient descent, right? So in the stochastic gradient descent, that is known as the implicit regularization, where we are not doing in we are not using stochastic gradient descent as an explicit technique for regularization, but when you are applying the stochastic gradient descent, the regularization would also happen because the values are because the updating happens with some different values, and we are using moving away from its original path, so that you would have much more higher probability of moving away from a local minima compared to the batch gradient descent. So this would be a much better approach of learning uh, when it comes when you think in terms of moving to an global solution, right? So the problem is having noisier updates. The positive side is that but this can escape a local minima with a higher probability, right? So, but the problem with this stochastic gradient descent is that when you have a large data set and when you find that the instability is too high, right? So you may not be able to move towards the optimum point, right? In that case, because if the variance is too high when it comes to the data points, you would not be able to update each of the data point for, for updating the parameters. In that case, you can use not a single data point for each update, but use a mini batch, right, of data points for updating the parameter. So that is known as the mini batch gradient descent. So which is an intermediate uh, strategy in between batch gradient descent and stochastic gradient descent, right? Something in between batch gradient descent and stochastic gradient descent, where instead of having the whole batch, you are using only a small batch, mini batch in the data set, and you are not either using individual data points, so that it would not be having it would be having a very uh, noisy update or the rough path. So mini batch gradient is the something of the best in between these two worlds, right? Using the whole batch for updating the parameters, or using single data points for updating each of these parameters. Stochastic gradient is. So this one is generally mini batch gradient is generally used for in most practical cases. And the problem with stochastic gradient descent, as we have discussed, is about the problem of uh, oscillation, higher oscillation from its original movement path, right? For example, say that you want to move in this direction, but the stochastic gradient descent would be like here, move here and there, right? So suppose that instead of using uh, many data points, if we can we already know that, right? So we have done several training iterations, and now you know the direction that your learning process is moving towards, right? So that is like the momentum of a physical particle, right? So if you take a certain particle or person, when although they are moving here and there around its original path, after some time you will understand that this particular person or the particle is moving towards this direction, right? So its momentum is in this direction. So if we can add the momentum term into this learning process, then you would not be having to move too much far to move far away from its original path too much when you add some momentum term into this data point, right? So that is the technique known as the stochastic gradient with momentum optimizer, right? So this zigzag inconsistent directions, uh, which is causing slower convergence, can be minimized using the momentum concept, right? So in that case, what we are trying to do is we are accumulating a velocity term, right? So when you are moving here and there, we are calculating the velocity. Velocity means the direction which you are moving, and we are accumulating that particular value, and we take the averages of the past gradients, right? So that is so we are taking the running average of past gradients, and this is known as the accumulating a velocity term, right? So in actually what we call it as accumulating the velocity term in this learning process is actually we are taking the past gradients running average, right? And then we keep that in mind, or we keep that in a variable of the value of this velocity term, and that means we are taking that particular variable which is representing the overall direction that the learning process is moving towards, and we are using this term for the learning process, or of determining the direction of learning in this algorithm. So this is the stochastic gradient descent algorithm with momentum, right? So in each time step t, we calculate this velocity term, right? So where we started with 0 in the initial value, because the initially we don't have any velocity, right? So we start with 0, like in a real physical particle, right? So we start any particle from the velocity 0, and then we are increasing the velocity, right? So in order to calculate this velocity, we are using the previous timestamps velocity multiplied by this gamma, or the momentum coefficient, right? So this momentum is some this momentum coefficient is some value which is between 0 and 1, right? So you are using this momentum coefficient and using some proportion of the previous velocity and multiply it with this momentum coefficient, and then we apply the then we add the learning rate times the gradient, right? So we, instead of using the learning, so this is the update rule for this, but for the parameters, right? So in this case you can find, instead of just uh, reducing the, so when it comes to the pure gradient descent, we are just using this term as this Vt, right? But in this case, instead of using this learning rate times gradient term, we are adding some previous momentum, right? So, or the previous velocity, t minus 1 time t minus 1 time step velocity multiplied by some coefficient which is between 0 and 1, and we are taking the historical values that we have remembered to now and add it to the to this gradient descent times gradient times alpha term, right? So in that case, if when we are using a single data point, this value would be moving to a very random direction, because this is related to a single data point, but we already remember where we were moving, right, in the previous time step. So you, because you are adding some proportion the previous time steps velocity, this overall velocity would not be moving far away from the original uh, the earlier time steps path, right? Sorry, because of that, uh, this learning process would be much more focused to the overall path that we were moving in the past or historical data points, right? So this would avoid the requirement of using multiple data points, but because it has this Vt minus 1 has the memory of the velocities that we have used in the previous data points, uh, this velocity would contain higher proportion of the previous velocity, so that it would be moving towards the original direction instead of moving here and there in this due to this gradient term calculated for a particular data point, right? So this is a very good improvement when it comes to the gradient descent algorithms, especially when we are using stochastic gradient descent learning, right? Where you are using a single data point for updating the parameters. So there's another uh, optimizing algorithm which is known as the adaptive gradient descent algorithm, right? So in this is simply known as AdaGrad, right? AdaGrad. So in this case, in AdaGrad, it adapts the learning rate of each parameters individually, right? And based on the uh, cumulative sum of squares of past gradients, right? So in that case, what we are trying to do is we are uh, taking the second derivative of the gradients, right? I take the not the uh, cost function theta of theta and its derivative, but its square, right? No, not the second derivative. Means that we are taking the square of this gradient term and we are adding it to the previous gradient, right? Gt minus 1 and get the gradient term, right? So that gradient term is used for reducing the overall alpha value, right? So when it comes to gradient descent, we are only using this alpha term, right, for updating the parameters, right? And remember theta in the original gradient descent, we are using theta minus alpha times this gradient, right? But when you are having a higher gradient, right, and when you find that the previous gradients are also high, right, then you get the gradient term which is higher in size, right? Is this value. So when this GT is too high, your alpha overall learning would get much slower because this alpha would get divided by the square root of GT, right? So the idea is that when the gradients are getting larger, right? When this gradient theta of j theta is getting higher, you should learn slowly, right? Because the gradient is too high. If you move too faster, then you would miss the optimum point, and it may drive to divergence, right? So because of that, when the gradient is too high, you have to this would automatically reduce this learning rate, right? So in the original gradient descent algorithm, we were just using the alpha term, but in this case, we are dividing this alpha term with the square root of uh, gradient term, right? So in the only difference is that we have used this epsilon term, which is a very small number, to avoid this value being divided by zero problem, right? So just forget, if you forget this epsilon term, what we are really trying to do is we are trying to divide this alpha term with the square root of uh, gradient, so that for higher gradients you would have very high value for this value, so that this learning would be much slower for these particular parameters, right? So for different parameters, different learning effective learning rate. So if this is the real learning rate, right? And this would be the effective learning rate, right? The really effective learning rate for that particular theta update, right? So this effective learning rate would be much lower when the gradient is getting higher, right? So that is the AdaGrad optimization algorithm. So instead of using the uh, when it comes to this is the RMSProp algorithm, or the root mean square propagation algorithm, right? This is also similar to the AdaGrad, or the previous adaptive gradient algorithm, right? Which is also learning, uh, having different adaptive learning rates for each of the parameters individually, right? That is the difference. Mm, This is same as the AdaGrad, but instead of just using the gradient updates, we are using the moving average of the squared gradients in the RMSProp algorithm, right? So in that case, uh, because we are using moving averages, this learning rate, the effective learning rate, would not become too small as well, right? So when the learning is getting too small, these values will not get updated, right? So then the learning will not happen, right? So in the AdaGrad, that problem is there. So instead of using the so using the directly the gradient, we are using this moving average of the squared gradients, right? Which is a which is an exponential moving average algorithm for calculating the gradients, right? So when it comes to the earlier case, this is the GT, right? And this is GT minus 1, the previous time steps gradient. And this is the square of the gradients, right? But in this case, this instead of gt, we have g square t, the expected value of g square t, right, which is applied on the expected value of g square t minus 1, or the previous timestamps g square, but not the same value, but which is multiplied by this beta value, right? And this value, or the square of this gradient is multiplied by 1 minus beta term, right? So now, compared to the AdaGrad algorithm, we have added this new beta term, which is known as the decay rate, right? So instead, in this case, we are using this. We have to define this hyperparameter beta, right? Which is around typically around 0.9. Actually, we can tune this hyperparameter as well, and using this decay rate hyperparameter, you can change how much the moving average of the squared gradient of the previous timestamp is affecting the current moving average of the squared gradients is affected using this hyperparameter beta, right? So that means when the beta is high, this proportion would be high, and this 1 minus beta would be lesser, right? So the current effect on the uh, square of this gradient would be lower when the beta is higher, right? Similarly, when once you calculate this value would be used here, right? So this is the same value that we have calculated, right? Epsilon is same as the earlier value, right? And this is the same gradient, right? The only difference between the AdaGrad and the RMSProp is that RMSProp is using uh, exponential moving average of these uh, gradients, right? Squared gradients. So RMSProp is kind of an updated version of AdaGrad, but the downside is that now you have another hyperparameter beta to be tuned, right? Okay, now we have learned about several versions of several improvement forms of the gradient descent algorithm, and this is like the current pinnacle of the optimizers, or the gradient descent based optimizers, which are used for any form of deep learning algorithm when it comes to most of the problems that we have in our hand, right? So that is known as the Adam optimizer, right? So this is not a name that has come from a person named Adam, right? Actually, this Adam is relevant to the name as adaptive moment estimation. This Adam optimizer is a combination of the concepts of momentum and the concept of RMSprop, right? So in the momentum optimizer, we were learning that we are using the moving averages of gradients, especially when you are using the stochastic gradient descent, right? So we keep the uh, moment or the velocity in our mind, and then we update proportion of them in the previous time steps velocity for calculating the momentum, right? And when it comes to RMSprop, we are updating the gradients using the exponential moving averages of the previous squares of the gradients, right? So this Adam optimizer is a combination of both momentum and RMSprop algorithms, right? So this is the so in this slide I have included everything related to the Adam optimizer. Right? In this case, what we are trying to do is we are trying to first calculate the exponential moving averages of the first moment of the gradients, right? That is empty, right? This is the first moment of so we are taking the exponential moving averages like in the RMS prop, but for the first moment of gradients, right? This is the first. This actually this is simply the gradients of the first moment. Means we are just taking the gradients. We are taking the exponential moving averages of the gradients, right? For that we have to define this beta 1 hyperparameter, right? Uh, like in the RMSProp, we are taking the beta 1 times momentum of the previous time step plus 1 minus beta times the gradient term, right? So we take the gradient from the history. We are calculating the moment of the this momentum of the gradients using the exponential mean average using this beta 1 hyperparameter, right? So this beta 1 is the hyperparameter used for exponential moving averages of the gradients, right? Similarly, you are calculating another term known as the second moment of the gradients, which is known as the we take the squares of the gradients, and then we take the moving averages of these gradients, similar to the RMSProp, right? In that case, we have to use another hyperparameter known as beta 2, right? Beta 2 times Vt minus 1 plus 1 minus beta 2 times the square root of gradients. Remember that V2 is not related to the velocity that we have used in the momentum, right? So this is a completely different one, right? So this is about the second moment or the mean exponential mean average of the squares of the gradients, right? And which is different from the exponential moving averages of the pure gradients or the first moment of the gradients, right? So that is for differentiate between M and T for the first moment and second moment we have used for the first moment we have used MT, and for the second moment we have used VT, right? So this VT is not about the velocity, right? So not confused between the VT that is used for the momentum uh, momentum calculation, right? So this is a different value, right? So this is the first moment and this is the second moment, right? Or this is the moving exponential moving average of the gradients, and this is the exponential moving average of the squares of the gradients. And but when we are implementing this one, we have to initialize this first moment and the second moment as well, right? Because when we are starting the learning process, we are initializing MT or the first moment to 0. The second moment is also to 0, right? Because of that, in the earlier phases of the learning process, this MT and VT are not unbiased estimators for moments, right? So we have to make them bias corrected, right? So we calculate the bias corrected first moments of the estimate known as MT, and the bias corrected second moment of the estimate known as VT hat. Sorry, first bias corrected first moment of the estimate as MT hat, and the bias corrected second moment of the estimate as VT hat, right? So this is how we calculate. For the first moment of the uh, 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 exponential moving average of the moments, we calculate by dividing this biased estimator by 1 minus beta 1 to the power t, right? Similarly, in order to calculate the second moment of the or the unbiased or the bias corrected uh, version of the estimator for the second moment of the uh, gradients, we calculate it by dividing the original biased uh, second moment of the gradients by 1 minus beta 2 to the power t, right? So what really happens is that why so the first we have to know why we call these MT and VT are biased estimators, right? So why we call them as bias is because we are initializing them to 0, right? So in the earlier phases of the learning, these values are biased towards 0, right? So in order to remove that bias, what we are trying to do is we are dividing it by the, we are taking the beta 1 and take to the power t, right? So when you are taking to the power t in the earlier phases, the t is equal to, t is close to 0, right? So the beta 1, we say that beta is a decay rate which is the first moment, which is typically closer to 0.9, and the beta 2 is decay rate for the second moment estimate, which is closer to typically to 0.999, right? So once you take the that kind of value related to, or if you take beta 1 and take to the power t, if you take 0th power, right, uh, this should be like this should almost close to 1, right? So 1 minus a value very close to 1 would be having a very smaller value, right? When the in the earlier stages of the algorithm, this t would be very closer to 0. So this value would be very small, right? So when this value is very small, uh, this value uh, would be very high, right? But sorry, it would be the other way, right? So when you are having a very smaller uh, value for t, right? That means we will be having a much a smaller value, so that mt would be okay. Let's think about that. When t is very small, right? Uh, so if you take the t is equal to 0, that means for the first in the first iteration, right? When t is equal to 1, t minus 1 would be equal to, or if t is 1, right? So it would be like 0.9, right? So it would be like 1 minus 1, 0.9 is 0.1, right? So zero point 0.1 mt is divided by 0.1. If the t is very large, right? So if there are many iterations that we have passed, say it is like t equals 100 or something, then 0.9 to the power 100, it would be a much smaller value, right? So then it would be 1 minus smaller value would be almost equal to 1, right? Uh, so then mt would be larger. So the value of the mt would be having a, this mt hat would be much larger, much more closer to mt1 when we progress through the algorithm, right? So in the earlier phases, in the earlier iterations, this mt would be very close, very small, right? So in that case, mtu would not be affecting that much, right? So in Adam optimizer, what we really trying to do is we calculate the second moment optimizer like the RMSProp, which is VT hat, right? Similarly, by taking the VT value divided by the beta 2's tth power, and when we are applying it as the, like in the RMSprop algorithm, right? And instead of using the same gradient, we are using the uh, exponential, or the we are using the exponential moving average and take that values uh, unbiased estimator mt hat and use that mt hat as the gradient of this algorithm, right? So this is a much more improved version of gradient descent algorithm, where instead of using the gradient value, we are using the unbiased estimator of the exponential moving averages of the gradients, and instead of using the learning rate, we are using the learning rate divided by the uh, second moment of the or the sorry the unbiased estimator of the second moment of the uh, gradients to uh, adapt the learning rate, right? So this is the Adam optimizer which is used currently in most of the deep learning algorithms, right? And when we are defining, you are writing deep learning algorithm also, generally you can use Adam optimizer without much research in it, right? And because of that, this is the most popular mm, optimizer that is used in these days, right? And there are some advanced, even more updated versions of Adam optimizers like ADMX and so on. So maybe you can use them for uh, different requirements as well. But like the ReLU activation that we are using for almost all the uh, deep learning activation functions, you can use the Adam optimizer for most of the uh, optimizers in deep learning, right? That is all for the today's lesson. If you have any questions, you can ask.